Okay, in this video we're going to look at section 4.1 in the text, and it's called exponential functions. The first thing your book does is give you the definition of an exponential function, and basically we just want you to realize that it's a function of this form right here, and this is going to be numerical and it's not going to be 1, because 1 raised to any power is just going to give you 1. And that is a constant function. And so basically you know it's an exponential function if the exponent is the variable. Okay. Alright, and then they move on to some of the properties of exponents, and here they are. Basically anything raised to the 0 power is going to be 1, except 0. 0 to the 0 power is indeterminate. Here you've got two bases with two exponents. We're going to add the exponents together. Here, when we're dividing two bases, you're going to subtract the exponents. Here, if you have one base and it's raised to two exponents, they get multiplied. Here, if you have two or more bases raised to the same exponent, you can raise each individual base to that exponent. Here, we're dividing two bases raised to the same exponent, or we can take the numerator and raise it to the exponent and then divide it by the denominator raised to that exponent. And then finally, to relieve yourself of negative exponents, you can just take the reciprocal of the base and then the exponent becomes positive there. Okay. Alright, so example 1, we're going to use the properties of exponents to simplify each expression. In part A, we have 3 to the second power times 3 to the third power. Alright, if we use our properties, I have a base times a base, and they're the same, and I am supposed to add those exponents together. So 3 to the power of 2 plus 3, this is 3 to the fifth, and if we put that in our handy dandy calculator, it should give us 243. For part B, we have 3 to the second power times 3 to the negative 1 power. This is the same property as in part A. We're supposed to add those exponents. So we're going to have 3 to the power of 2 plus negative 1, which is going to be 3 to the first power, which is just going to give me 3. And then in part C, notice this time I only have one base. I still have two exponents, but I only have one base. This is the property where we multiply those exponents together. So this is 2 to the power of 3 times 2, or 2 to the power of 6, and if we put that in our handy dandy calculator, it's going to give us 64. Okay, example 2, we're still using those properties of exponents, so we're going to simplify these expressions. The first one has a negative exponent, and so the property is, if I have a base and it is raised to a negative exponent, what I'm supposed to do is take the reciprocal of that base, and the reciprocal of 1/2 is 2 over 1, and raise it to the positive power there. And so we're going to have 2 over 1 times 2 over 1 times 2 over 1. That's going to give me 8 over 1, which just simplifies to 8. In part B, I'm dividing. I have the same base here. This is where I'm going to subtract the exponents. So we have 2 to the power of 2 minus 3. This is going to give me 2 to the power of negative 1. There's that negative exponent. So we're going to take the reciprocal of the base. The base is 2 and the reciprocal is 1/2. And then we're going to make that a positive power on there. Which, since it's a 1, we really don't have to write it in there. Okay. Alright, and then for part C, now I'm going to kind of do the reverse of one of my properties, because I have 2 to the power of 1/2 times 5 to the power of 1/2. My bases are not the same, but my exponents are. And so that means I can rewrite this as 2 times 5 to the power of 1/2. Okay. And then we can simplify that, because 2 times 5 is 10, and so this is 10 to the 1/2 power. And we already know that when we have a 1/2 power, that really means, in this case, we have a square root. So this is the square root of 10 simplified. Example 3 here is dealing with applications of some of these exponential functions. In living organic material, the ratio of radioactive carbon isotopes to the total number of carbon atoms is about 1 to 10 to the 12th power. When organic material dies, its radioactive carbon isotopes begin to decay with a half-life of about 5,715 years. This means that after 5,715 years, the ratio of isotopes to atoms will have decreased to 1/2 the original ratio. After a second 5,715 years, the ratio will have decreased to 1/4 of the original, and so on. The formula for the ratio R of carbon isotopes to the carbon atoms is R is equal to 1 divided by 10 to the power of 12 times 1/2 to the power of T divided by 5,715, where T is the time in years. And we're going to find the value of R for each period of time. In part A, 5,000 years, in part B, 15,000 years, and in part C, 30,000 years. So essentially what we're doing here is we have our formula given to us right here. And this is telling me to figure out what R is equal to, and each one of these represents a time period. And so for each case, we're just going to take that number and plug it into the exponent t, and then put this in the calculator and see what we get. So for part A, R is going to be 1 over 10 to the power of 12 times 1/2 to the power of 5,000 divided by 5,715, and we'll put that in the calculator, and we'll round this out to 3 decimal places and see what we get. And my calculator has this in scientific notation. I have 5.453 times 10 to the power -13. Alright, in part B, we're going to do the same thing. We're looking for R. So we'll have 1 over 10 to the power of 12, times 1/2 to the power 15,000 divided by 5,715, and we'll put that in the handy dandy calculator and see what we get. And again, I'm in scientific notation with 1.621 times 10 to the power -13. Okay. And then finally we're going to put in the 30,000 years and see what happens. So we'll have 1 over 10 to the power of 12 times 1/2 to the power 30,000 divided by 5,715, and we are going to put this in the calculator and see what we get. And I am again in scientific notation with 2.629 times 10 to the power -14. Okay, the last thing we want to do is work on graphing some of these exponential functions, and so the next 2 slides tell you some of the properties and how the transformations work. Okay, so things we need to know. Alright, if your base is bigger than 1, then your function is increasing, and we call that exponential growth. If your base is between 0 and 1, so that means it's a proper fraction where the numerator is smaller than the denominator, then you have a decreasing exponential function, which we call exponential decay. Okay, all of these exponential functions will have a domain from -infinity to +infinity. The range will go from 0 to infinity. Notice we have the open circle, the open parentheses right here. That's because of this next line right here. The x-axis is a horizontal asymptote for the parent function. Okay. And then this next one, these 2 that I'm starring, we're going to use when we try to graph these. These functions are going to pass through the point 0, 1, because when you plug 0 into the function, any base to the 0 power is going to give you 1. And it also goes through the point 1 and whatever your base happens to be, because when you put 1 into your function, the base raised to the first power is just b, your base. Alright, on our next slide, we're looking at the transformations. Here is what our general function is going to be looking like if it has any transformations going on. Okay, h up here in the exponent is going to shift you to the left and to the right. Okay, now when h is negative, your graph is going to be moving to the left, and when h is positive, it's going to be moving to the right. Now, please remember, x always lies and y always tells the truth. And what I mean by that is we're going to check this sign right in here. This is a negative sign, and so this h is actually positive, and we're going to be moving to the right. If this were a plus sign, then h would be negative, and we would be moving to the left. So when you're trying to figure out your transformation to the left and to the right, you're going to do the opposite of the sign that you see up here in between the x and your horizontal movement. Okay. Next one, k, that's the number back here either added or subtracted to your exponential factor over here. And it's going to move everything up when k is positive, it's going to move everything down when k is negative. And then this little guy right here, if you have a number being multiplied by that base, that's going to tell us a couple of things. Number one, if it's a negative number, then there's going to be a reflection across the x-axis. And then number two, it's going to tell us if we have a vertical stretch or shrink. Okay, now what I want you to be careful of is if you have a function that looks like this, where you have 2 times 3 to the power of x, this is not the same thing as 6 to the power of x. Because according to our order of operations, we have to do this guy first, then we can multiply it by 2. So be sure you don't get these two mixed up. Alright, let's see if we can graph this thing. We want to graph f of x is equal to 5 to the x power. Now, keep in mind, all of these exponential functions are going to be going through the point 0, 1, and also 1 and whatever our base happens to be. Now the base, in case you didn't know, that's the number that is raised to the exponential power. And in this case, our base is going to be 5. That means that our graph is going to have to pass through the point positive 1 and positive 5. Alright? Another thing that we knew based on our properties back here is that there is a horizontal asymptote. Now, asymptotes are imaginary lines that your graph approaches, and normally it doesn't cross. It usually just approaches it and then runs right along beside it for a while. Sometimes it'll cross over, but in these exponential functions, they will not be crossing over. Okay? Alright, so I have a horizontal asymptote on the x-axis, and the equation for that is y is equal to 0. And I'm going to go ahead and sketch that in right here, my imaginary dotted line, like so. And I'm going to plot my 2 points. 0, 1 is going to be right here, and positive 1, positive 5 is going to be right here. And so this exponential function is going to be moving off in this direction on this side, and then the other direction, it's going to move this direction toward the asymptote, but we're never going to go underneath the x-axis there. And so this is what my function is going to look like. Okay, here's our last example, number 5. We're going to sketch the graph f of x is equal to 2 to the negative x plus 1. And I'm going to switch this around a little bit because right now the base is not extremely obvious to me. So let's rewrite this. We've got that negative exponent in there. Let's make it a positive exponent. That means we take the base right here, take the reciprocal of it, and then put that power on there as a positive power. That means we can rewrite this as f of x is equal to, the reciprocal of 2 is 1/2, and then the exponent, which is negative x, now becomes a positive x. And then that plus 1 back there is not going to be affected. So this is actually the graph that I'm going to draw. Okay, now the parent function here, and I mentioned that a slide or two back when I was talking about the parent function. The parent function is a basic function. It gives you the basic shape. And so this is about as vanilla as it can get because nothing's been done to it. There's no horizontal shift, there's no vertical shift, there's no stretch or shrink. It's just the one that's there, and it is stripped down as far as it can be. Okay. Now in our case, the parent function is going to be y is equal to the 1/2 to the power of x. Okay. That's our parent function. And that's actually going to help me over here. I like to keep track of when I'm doing my graphs in a chart. I know that the parent function is supposed to go through the point 0 and 1, and it's also supposed to go through the point +1 and whatever our base happens to be, and we said the base is going to be 1/2. And I know that the parent function has a horizontal asymptote where y is equal to 0. Okay? Alright, if I take a look at my equation back here, there's no horizontal shift because there's nothing up here added or subtracted to the x, or up here either. There is a vertical movement though, right here, the +1. That means everything moves up 1. Alright, now I have an x coordinate and then I have a y coordinate. If I'm moving the entire graph up, that means I'm going to leave x alone and I'm going to be adding 1 to the y coordinate. And so my new ordered pair is going to be keep your x and then add 1 to y. So we're going to keep 0, and then 1 + 1 is going to give me 2. We'll keep the 1, and then 1/2 + 1 is going to give me 1 1/2. And this is a y equals. So remember, we keep our x, which we don't have, and then I'm supposed to add 1 to y. So 0 + 1 is going to give me 1. That means my asymptote is going to be moving up also. Which makes sense because when I have a vertical movement, I'm literally taking the entire graph and I'm picking it up and moving the whole thing. And so if the horizontal asymptote is down here at 0 and I'm picking the whole graph up, the horizontal asymptote has to move up too with the rest of the graph. Okay. These are the points we want to draw right here, and then we want to put that asymptote in there. Well, actually, I'm going to do that first. Alright, so y is equal to 1 would be an imaginary line drawn right here. Alright, our point is going to be up here at 0, 2. And then our next point is going to go at +1, +1 1/2, which is a little bit below right here. So this one's not quite as easy to see, but your point right here is actually higher, which means that our graph is going to be rising over here on the left and then kind of flattening out over here on the right, moving toward that line y is equal to 1. So this is what our graph is going to look like.